Okay, folks. Now we are officially cooking with gas. We've defined sampling distributions of the mean, of proportions, of the variances, sampling distributions of any statistic, really, if we wanted to talk about it. Central limit theorem, which is what we're going to talk about today, we are not going to prove it. I actually had to prove this in some graduate work. It's no fun. It would take us a week to do it just to get the mathematics where we needed it to be. And it requires calculus and a number of other techniques that we just don't have time to discuss, especially for those of us that don't have calculus. Excuse me. However, this is really where the rubber meets the road. It's because of the central limit theorem, which I'm about to show you, which we're about to talk about, that we are able to do everything that we're able to do in what are called parametric statistics, or statistics around population values such as mean, mu, standard deviation, sigma, et cetera, et cetera. All right, but first, let's do a little exploration. I'm going to show you, this is an applet that comes with the disk in your book. So I'm going to go ahead and pop out of the book real quick. All right, I'm going to show you something really cool. All right, so first things first, all that we're going to concentrate on is this little bit right here. All right, but I want to show you what happens. I want to prove to you what happens. Unfortunately, this applet only has things for sample means, not for sample standard deviations. So it's very difficult to do sampling distributions around standard deviations with this applet. In fact, it's impossible. It also doesn't talk about sample proportions, but I think that this will give you an idea. Okay, so here's what we're going to do. We're going to pick a sample of size n equals 10. Now notice I can drop this down and pick 30, 50, and we'll play with all of those. But for now, let's just start with 10. Okay, so think of this as randomly selecting samples. Now, in class, we're going to discuss, should we do this with replacement Ripley? Should we allow samples to keep jumping back into our samples of size n, or should we exhaust all of them? There are arguments for both, and we'll discuss it in class. Okay, but for now, let's just assume that we're just going to keep grabbing random samples of size 10. So there can be a certain degree of replacement, although it's not very likely. Okay, and we're going to do this. Now this n is a little misleading. This is not saying that n is the size of our population. What it's saying is we're going to do this 1,000 times, okay? And then we're going to look at what the distribution looks like, or I guess that's 10,000. But I'm going to start slow. I'm going to walk you through it. I'm going to do it one time, okay? And watch what happens. All right, we have a mean, which is between 0 and 50. Okay, oh wait, I've got some more explaining to do. In this case, the population that we're drawing from is bell-shaped, or it's normal. Okay, it's got a mean of 25. We don't care about the median, and it's got a standard deviation of 8.2239. Okay, so what I did is I did this one time. I grabbed 10 things. All right, we don't even care what we're asking these. I don't know, a number of 0 to 50. The number of times last month you kissed your mom on the face. I don't know, something silly, right? We took the average number, and here it sits. All right, now I'm going to do it 100 times. I'm going to do it 1,000 times. I'm going to do it 10,000 times. Look at that. Isn't that cool? Now, really, I've done it 11,101 because I scrolled through. Now, I'm going to keep doing this. When I hit sample, it's going to keep just adding to this distribution. Watch. So, look at that. Becomes more and more and more normal. Now, I want you to notice something. The mean of this distribution is 25.0003. The mean of the population is 25. Now, the standard deviation of this population is 8.2239. The standard deviation of this population, or of the sampling distribution, is 2.6. So let's go 8.2 and 2.6. I'm going to write those down just for fun, okay? I'm going to write the mean is 25, and the standard deviation, what is that? Let's just call it 8.2. Okay? Now, I'm going to introduce some notation here. The mean of the means, okay, that's really the mean of this distribution, is 25 for all intents and purposes. Hey, it's an unbiased estimator. Who knew? The standard deviation of the sampling distribution is 2.6, or approximately 2.6. Okay? Excuse me. This is sometimes referred to, by the way, as the standard. I know the vocab in this can be a little daunting, but again, just make flashcards, don't be afraid. The standard error of the mean. Think about it. Standard deviation is really just an error measurement. All right, so the standard error is the error that comes from the sampling distribution, in this case, of sample size n equals 10. Okay, so this was when n equaled 10. We're just writing some stuff down. We're having some fun here. Let's say when n equaled 5. Okay, now let's go through it again. Only we'll start with 100 this time because that was simple. Well, that doesn't look very promising, does it? Let's go 1,000. Oh, hey, whoa, what's going on here? Let's say 10,000. Now remember, we're just focused on the green one. Focus on the green one. All right, now I'm going to do this a few more times, and let's watch what happens. Look at what that curve starts looking like. Look at the mean. 25, 25. Standard deviation, 8.2. Standard deviation, 3.7. Let's write that down. So I'm going to stumble over here. Whoops, I don't want that. What's going on here? Let's do bamboo. All right, so when n equaled 5, the mean of the means was 25. To be expected, it's an unbiased estimator. That's just awful. Whoops, sorry guys. I'm going to try that again. Let's make this just a little prettier. All right, so the mean of, so this is my sampling distribution, my standard error of the mean, or the standard deviation of the sampling distribution, was 3.7. Huh, something fishy's going on. Well, let's play some more and see if we can figure out what's going on. All right, now we're going to go n equals 50. We'll keep it at 10,000, I think. And remember, we're just paying attention to means. Watch this. Booyah. Booyah. Keep going. We'll go out to like 90,000. And we'll go to 60 because not a whole lot else is happening. Look at that. The mean is 25. The mean is incredibly close to 25. I want to get it to 25. I'm stubborn. Maybe we can't get it there. Oh, there we go. Yay. Or close enough for government work, right? And this, whoa, the standard deviation is way smaller. All right, let's write it down. So when n equaled 50, the mean of the means, or the mean of the sampling distribution was, boy, big surprise, right? It's an unbiased estimator. The standard error of the mean, or the standard deviation of the sampling distribution, in this case was 1.16. Just call it 1.16, just to keep it simple. I guess I could have just done 1.2. Huh. All right. Now, remember, well, maybe we talked about this, maybe we didn't. But regardless of the shape of the population, let's make it skewed. All right? Look at this big, fat skew to this thing. Let's go back to our 5. All right? And I'm going to do this 10,000 times. All right, remember sampling distribution. So I'm gathering 10,000 samples of size 5, and I'm finding their mean. Watch this. All right, remember, I'm sorry, the suspense is building. I can't believe it. It's skewed. Oh my God, I hope it, oh my God, look at that. We'll hush my mouth. Let's see what the mean gets to. The mean of the population distribution is 15.529. The mean of the sample means was 15.529. It just keeps getting closer. Oh, that got a little out of hand. 15.53, 15.52. Look at that. Isn't that crazy? The standard deviation. Whoa, what did I just do? The standard deviation. Oh, I can't undo that. Let's reset that. Reset. And we're going to go. Let's go Bell. Let's go. That was crazy. There, 15.529. Sample. Sorry, guys. That's what happens when all hell breaks loose, right? 15.5 to 15.5. Let's get it up there a bit. Let's get it closer. That's close enough, right? Standard deviation is 12.5. Standard deviation is 5.58. So wait a second. Let's go over a page. All right? Now, We know that the mean of the population is 15 point, this is, by the way, arbitrarily chosen, 529, right? We know that the standard deviation of the population is 12.51. The mean of the means, well, we know it's an unbiased estimator, so we know it heads for at least 15.529. And the standard error of the mean, or the standard deviation of the sampling distribution, oh, this, by the way, was when n equaled 5, is 5.58. Let's do it one more time. I think you're starting to get the idea here. If I go, let's go 50 this time. Watch this. It doesn't take half as long. Look at that. Look at the mean. 15.52, 15.5. It's just huddling right around. Look at that, 15.529. Standard deviation, we'll write this down one more time because we'll use it later. When n equaled 50, I ended up with the mean of the means, we know is going to be 15.529, and the standard error of the mean ended up being, that's crazy, 1.7658. So notice, I'm going to blow this thing up real quick. Notice, let's do some observations here. For all of it, because the mean is an unbiased estimator, we know that the mean of the sampling distribution is going to be exactly the same as the mean of the population. But look at what happened to the standard error of the mean. Let's see, when n was 10, it was 2.6. When n was 5, so when n was smaller, it was 3.7. When n was smaller, the standard error of the mean grew, and when n was 50, look at how much smaller it is. Hey, that was true over here too, wasn't it? When n was 5, standard error of the mean was 5.58. When n was 50, it was 1.7658. Now we're going to take those and we're going to put them in our pocket. But one more thing, we're not going to write these down. However, I do want to show you one more thing. Look, what if it's not skewed? What if it's not bell-shaped? What if it's uniform? This simply means that every data value between 0 and 50 has the same occurrence, has the same number. Everybody kissed their mom 75 times, sorry, the proportion of students that kissed their mom 0 times last week is the same as the proportion of that's just gross. I should come up with a different, you get what I'm saying. Leave me alone. Okay, ready? Sample means. Here we go. So n equals 50. So my sample size is 50, and I'm gonna collect 10,000 of those samples. Watch what happens. Oh my goodness! Look at that. Just like we promised, sample means distribute themselves normally. Isn't that awesome? Do it a few more times, and watch what happens. Look what we had for. Now we're up to what, 130,000, and we're getting real close to 25. So close that it could be argued if there's not a whole heck of a lot of difference. Okay? Okay, that was fun. Now look at the standard deviation. The standard deviation of the original population was 14.43. Standard deviation of the sample means was 2.0395. Isn't that fun? Okay? Now, let's go ahead and go back here and start defining what's really going on. All right.